Welcome to AI Paperslop. We are diving straight into FlowWAM, which stands for Optical Flow as a unified action representation for world action models.
That's a fascinating one.
It really is. And here is the core insight you need right out the gate. So for a long time, world action models, or WAMs, have tried leveraging massive pre-trained video generators to control robots.
Right.
But they always hit the exact same bottleneck. Aligning discrete numerical robot actions with the visual priors of a video model is just incredibly inefficient.
It's a huge problem.
Yeah. So the authors of this paper, they're from the Chinese Academy of Sciences, MBZUAI, and Alibaba. They solved this by utilizing dense optical flow as a unified video-native action representation.
It is such an elegant shift in thinking.
Definitely. They map optical flow into an HSV image format, capping the magnitude to maintain stability, and then they feed it natively into a 5 billion parameter diffusion transformer.
The 2.2 base.
Exactly. And this yields a dual-stream model operating as both a policy, which predicts flow that decodes into physical actions, and a world model, which uses flow to generate future video states.
And the best part is the pre-training.
Right. Because this architecture relies entirely on visual flow, the model can pre-train its motion priors on massive amounts of action-unlabeled, human egocentric video before it ever sees a single piece of robot data.
It fundamentally reshapes the architecture of physical control, honestly.
I mean, it has to, right?
Yeah, because instead of forcing a generative visual model to decipher this low-dimensional string of arbitrary numbers, this approach translates the physics of robotic action into the dense spatiotemporal language the model is already optimized to process.
Exactly. And to really grasp the utility of FlowWAM for those of you building embodied AI systems, I think we need to look at the mechanics of the pixel action gap.
That's the real hurdle they're clearing here.
Right. Because WAMs are conceptually the right direction for robotics. They encode continuous frame-by-frame motion.
Which makes them vastly superior for manipulation tasks compared to, say, vision language action policies or VLAs.
Yeah, because VLAs lean so heavily on semantic image language priors, but they often just fail to model the continuous physics of a scene. They don't get the geometry.
No, they really don't.
Yeah.
They're more like captioning models acting as controllers.
Right. But the problem with WAMs has always been injecting that control signal. Like if you take a 14-dimensional vector representing joint angles in a gripper state, and you simply concatenate that numerical token into the high-dimensional latent space of a diffusion model,
You're creating a massive manifold mismatch.
yes, you're just jamming numbers where they don't belong.
Well, think about the video diffusion model, right?
Yeah.
In this case, it's built on 2.2. It understands gravity, occlusion, momentum, all of that, entirely through the temporal evolution of pixel patches.
Exactly. It expects high-dimensional, spatially organized data.
Right. And a 13-dimensional joint vector has absolutely zero spatial resolution. So the network is forced to just, memorize this completely arbitrary mapping between a dense visual world and a sparse array of floating point numbers.
Which is so inefficient.
Extremely. And furthermore, those numbers are entirely embodiment specific. The joint space of a single arm Franca is functionally useless when applied to a bimanual ARX5 robot.
So researchers obviously recognized that concatenating raw numbers into diffusion latents was suboptimal, which led to the use of latent actions.
Right, trying to learn action codes directly from frame transitions.
Yeah, but latent actions strip away the spatially grounded cues necessary for millimeter-level manipulation.
They're too abstract.
Exactly. The abstraction removes the physical geometry of the task, and that failure cascaded into attempts to use visual actions, like rendering an embodiment mask or an action ray map directly over the image space.
Which has always felt a bit clunky.
Frankly, visual actions have always felt like a half measure to me. Providing a static spatial cue, like a brightly colored mask, indicating the robot's end effector, it's essentially giving an animator a static storyboard with a few directional arrows drawn on it.
That's a great way to put it.
Right, like it provides spatial localization, it tells you where the action is, but it lacks temporal derivatives. It tells you nothing about how those pixels are actually supposed to move across time.
A static mask is just a frame-level conditioning signal. It does not evolve jointly with the predicted future frames.
Right.
To effectively condition a video generation model, you need a temporally dense representation. You need something that records the continuous displacement of every single pixel in the scene across the temporal axis.
Which is exactly why optical flow is the perfect bridge here.
It really is.
Supplying optical flow is like handing the model a highly detailed per-pixel motion capture feed. It eliminates all the temporal guesswork. But, implementing this introduces a severe architectural constraint.
Yeah, the VAE problem.
Right, because you cannot simply hand a raw optical flow tensor, which is basically a 2D tensor of U and V displacement vectors, straight into a pre-trained video model.
No, you'd break it.
Hmm.
The foundational model here is 12.2 Ti2V5B, right? It's a pre-trained image-to-video diffusion transformer. That architecture relies on a frozen causal variational autoencoder, or VAE.
And that VAE is designed strictly for standard RGB image distributions.
Exactly. So if you pass raw U and V tensors, which, they have arbitrary and unbounded numerical ranges, if you pass those into the convolutional layers of that frozen VAE, you will trigger massive activations.
Just off the charts.
Yeah, the latent representations will blow up and the diffusion process will just output complete noise.
So the authors had to map the flow field into an HSV image format just to stay within the VAE's expected manifold.
It's a really clever hack.
It is. They take the direction of the pixel's motion vector and map it to the hue channel, and then they take the magnitude of the motion and map it to the saturation channel. But the technical nuance that really makes this work is the clipping.
Right, the 25 pixel cap.
Yeah, they explicitly cap the magnitude at a 25 pixel displacement.
Because capping that displacement is critical for network stability.
Mm-hmm.
Like we said, the VAE was trained on bounded color spaces. By clamping the flow magnitude to 25 pixels and then normalizing it within standard channel bounds, they guarantee the resulting tensor mimics the statistical distribution of a standard RGB video.
Albeit a very weird-looking one.
Oh, visually, yes. A highly saturated, fast-moving video.
Yeah, and I do have to question how the network interprets this under the hood, though.
What do you mean?
Well, if we are mapping motion to color, we are essentially feeding the VAE these intensely saturated frames where a moving object looks like, I don't know, a shifting gradient of neon colors.
Right.
Does the VAE spatial frequency filter actually interpret these gradients as coherent motion, or is it just processing out of distribution visual noise that the downstream transformer somehow happens to figure out?
No, the VAE processes it seamlessly because optical flow, when it's formatted this way, retains the exact same spatial dimensions and edge coherency as the original video.
Oh, I see. So the shapes are all still there.
Exactly. The billions of parameters in the DIT that govern how textures, edges, and colors translate across space and time, they're immediately activated by this flow data. The network doesn't require a separate modality encoder to understand that a shifting patch of color represents an object in motion.
It just uses what it already knows.
Right. It utilizes its existing motion priors to propagate that patch through the temporal layers.
Wow. And that drastically reduces the parameter overhead, which we see directly in the architecture.
It keeps the model remarkably lightweight for what it's doing.
Yeah, because FlowWAM uses a dual stream setup. You have the standard RGB stream and this newly formatted flow stream, and they are sharing the exact same VAE encoder and the exact same massive transformer blocks.
Which is huge for efficiency.
Totally. The only additions are these really lightweight stream-specific adapters to handle the minor semantic differences between a true RGB frame and a flow-mapped frame.
And sharing those core transformer blocks is what makes this such a highly parameter-efficient, unified model. Because both modalities are processed in the same visual latent space, FlowWAM can operate natively in two specific configurations.
Right, world model mode and policy mode.
Exactly.
So in world model mode, you feed the network a sequence of clean target flow images. You are essentially providing a dense motion plan, and the model uses that flow as a conditioning signal to generate the future RGB video.
It renders a visually consistent, physically accurate future based precisely on the requested motion field.
It's beautiful, but for those of you deploying actual hardware, synthesizing a video is just a simulation.
It doesn't move the robot.
Right, you have to actuate physical motors. And this is where policy mode comes in. The model takes the current RGB state of the world and hallucinates the necessary optical flow to predict the future motion required to achieve a task.
It generates a visual blueprint of the required manipulation.
But wait, predicting a flow video still leaves a massive execution gap, right? Because a physical actuator cannot process an HSV pixel.
Not at all.
You can't feed a 25 pixel saturation value into a robotic joint. So if the output of this massive 5 billion parameter DIT is just a sequence of flow latents, how is this actually decodable for highly precise physical control?
Right. And the architecture addresses this through a dedicated module they call the Action Expert.
Okay.
The generated flow is strictly an intermediate, spatially grounded representation. Once the DIT outputs those high-dimensional flow latents, they are routed into this action expert, which is a significantly smaller 780 million parameter module.
So it's a fraction of the size.
Exactly. Its sole function is dimensionality reduction and modality translation. It applies spatiotemporal pooling to collapse the spatial dimensions of the flow latents while retaining the temporal motion cues.
Makes sense.
And then it passes that compressed representation through dense layers to output the 14-dimensional continuous joint action vector.
That is just a brilliant division of labor.
It really is.
The heavy lifting, the visual physics, the object permanence, the spatial relationships, all of that is handled entirely by the 5 billion parameter video model operating natively in the visual domain.
Doing what it does best, right?
It outputs a flawless visual motion plan. Then the action expert just acts as a targeted translator, converting that dense spatial plan into specific motor torques.
Yeah.
And to ensure that translator doesn't break down, they train the action expert using stochastic latent conditioning, right?
They have to, yeah.
Yeah.
Training the action expert purely on clean, ground truth flow latents would make the system highly brittle during inference.
Because the DIT isn't perfect.
Right. If the DIT hallucinated a slightly imperfect flow field, the action expert would encounter an out-of-distribution latent and just fail.
It would crash.
Yeah. So by mixing ground truth flow latents with noisy DIT-generated flow latents during training, the action expert learns to recover from minor flow prediction errors. It builds robust internal representations that map directly to the hardware.
And because the action expert handles that final translation into robot-specific joint vectors at the very end of the pipeline, the core DIT only ever processes visual motion.
Yes.
And that architectural separation unlocks FlowWAM's absolute superpower, which is bypassing the data scarcity bottleneck through massive unlabeled pre-training.
Which is everything in this field right now.
It is. Data scarcity is the bottleneck.
Yeah, data scarcity remains the primary constraint in embodied AI. If your foundational action representation requires joint torques, gripper states, or force sensor data, you are fundamentally limited to datasets composed of meticulously recorded, teleoperated robot demonstrations.
Which requires buying hardware, paying engineers to run space mice or, wear full VR rigs, and logging thousands of hours of incredibly expensive embodiment-specific data.
It's completely unscalable.
But Optical Flow doesn't require a single joint angle label. It is purely a calculation of pixel displacement between frames. So the authors bypass the robot entirely by using RFT?
Recurrent all-pairs field transforms.
Right. They use RFT to extract dense optical flow from raw, action-unlabeled human videos.
And RFT is highly effective for this because it computes multi-scale correlation volumes between image pairs and uses a recurrent neural network to iteratively refine the flow field.
Gets you really clean flow.
Very clean. And the authors applied RFT to the EgoDex dataset, which consists of massive amounts of egocentric video showing human hands interacting with objects in complex environments.
Just everyday stuff, opening doors, grabbing cups.
Exactly. There are no kinematics, no robot states, just raw visual data of human manipulation.
So they pre-train the model's motion priors on this massive ocean of human data. The FlowWAM architecture learns how objects react to force, how gravity acts on a dropped item, and how occlusion works when a hand wraps around a handle.
Just by analyzing the visual flow.
Yeah. It acquires a deep, generalized understanding of physical intelligence long before it is ever fine-tuned with the action expert on a specific robot platform.
Decoupling the physics prior from the hardware execution is a paradigm shift.
Really feels like one.
The dual-stream video generator masters the universal rules of motion through unlabeled human data. And once that foundational understanding is established, fine-tuning the action expert requires just a fraction of the domain-specific robot data to map that visual understanding to actual motor commands.
Now, the theoretical elegance of decoupling physics from hardware is super compelling, obviously, but the empirical results on the Robotwin manipulation benchmark are what really prove the architecture's viability.
The numbers are wild.
Yeah, FlowWAM achieves a 92.94% success rate on the clean settings. But the metric you really need to look at is the random setting, where objects are spawned in highly unpredictable poses and weird lighting conditions.
The hard stuff, right.
In that highly variable environment, FlowWAM achieved a 92.14% success rate.
A performance drop of less than 1% between a clean environment and a highly randomized one indicates profound visual robustness.
It's basically unfazed.
Yeah, the policy is not overfitting to specific object coordinates. It is genuinely understanding the scene geometry. And the ablation studies in the paper explicitly isolate the human egodex pre-training as the primary driver of this generalization in the random setting.
So the pretraining acts as a massive variance shield. And that robustness carries over to world model mode as well.
Oh, absolutely.
When evaluated on the World Arena benchmark, FlowWAM achieves a state-of-the-art UWM score, embodied world model score, of 63.71.
But the aggregate score almost obscures the most critical data point.
Right, the trajectory stat. FlowWAM drives an 18.4% relative improvement in trajectory accuracy compared to the best baselines.
That 18.4% improvement validates the entire premise of using optical flow as an action representation.
How so, exactly?
When you condition a generation model using numerical action tokens or text prompts, the trajectory control remains severely underspecified in the visual domain. The model might generate a video with high visual fidelity, maintaining background consistency, making it look pretty, but the robotic arm in the generated video will often drift. It completely fails to follow the physical trajectory commanded by the numerical token.
It just hallucinates its own path.
Exactly. But because optical flow provides a per-pixel motion field, it tightly steers the generation. It literally forces the model to obey the requested motion.
That makes total sense. And FlowWAM also topped the depth accuracy metric, confirming that dense flow provides a much richer spatial and geometric grounding for the model to denoise against.
It gives it physical anchors.
Right. And if you needed any more proof that the flow channel is the active ingredient here, the authors ran an ablation where they swapped the optical flow representation back to standard numerical actions, keeping the entire 5 billion parameter 2.2 architecture identical.
And the policy success rate immediately crashed to 69.8%.
Dropped off a cliff.
Yeah. This confirms that the closure of the pixel action gap is not merely a byproduct of scaling up a generic video transformer, but is causally linked to the dense flow representation itself.
I'm also anticipated the primary skepticism regarding decodability.
Sure, people always doubt if the latents actually mean anything real.
Right, like it is easy to argue that perhaps the massive DIT is just outputting aesthetically pleasing visual noise, and the 780 million parameter action expert is actually doing all the heavy lifting of figuring out the control policy from scratch.
Right.
But to disprove this, they plotted the flow prediction error against the ultimate task success rate across 50 different manipulation tasks.
And the analysis revealed a strong negative correlation of -0.81.
That's massive.
It is. The lower the flow prediction error, meaning the closer the DIT's hallucinated flow matched the actual ground truth of the required motion, the higher the physical success rate of the robot.
Which proves the point entirely.
Yes. This quantitative link proves the policy gains directly track the improvements in the visual flow prediction. The generated flow is a genuinely decodable causal blueprint for physical execution.
And they validated that blueprint on real hardware, too. FlowWAM wasn't just confined to a simulator.
Right, they put it on physical bots.
Yeah. They deployed the model on a single-arm Franca robot for high-precision spatial tasks like, stacking bowls and organizing drawers. And then they deployed the exact same unified flow representation on a bimanual Air X5 robot for complex, long-horizon tasks like folding a towel, which demands really tight coordination between two separate end effectors.
And transferring a unified action representation seamlessly across simulation, a single-arm platform and a dual-arm platform demonstrates that visual motion is fundamentally embodiment agnostic.
Which is the holy grail.
It really is. The network is simply predicting how pixels should move to achieve a goal, regardless of the underlying mechanical structure executing that movement.
So for the ML engineers listening, this research is a clear indicator of where embodied AI is heading. FlowWAM proves that treating robotic actions as dense visual motion fields rather than arbitrary symbolic tokens is the mechanism that will fully unlock the power of video foundation models for physical control.
And the engineering choices are just highly optimized.
Well,
using the HSV mapping bypasses the modality gap without requiring an entirely new VAE training pipeline.
super smart.
And the dual-stream DIT maintains parameter efficiency while natively supporting both world modeling and policy inference.
Yeah.
And most critically, tapping into action unlabeled human video via RFT fundamentally alters the scaling laws of robot learning.
We are abandoning the practice of forcing massive vision models to decipher human-engineered numerical arrays.
Thank goodness.
Right. By translating our control problems into the visual language these models already process natively, we are treating the robot not as a mechanical entity awaiting a joint command, but as a visual agent tasked with realizing a visual future.
Well said.
Before we wrap up, I want you to consider the broader implications of this architecture. If optical flow serves as a universal, embodiment agnostic translation layer between human video and robot action, we are approaching a massive disruption in how training data is acquired. If a model can map the complex physics of folding a towel simply by analyzing the pixel displacement of a human doing it without requiring a single joint torque label, are we about to see robotic foundation models trained almost entirely by ingesting millions of hours of YouTube? If we can run RAFT over endless egocentric tutorials and feed that flow directly into a DIT to learn generalized manipulation, it could render the painstaking, incredibly expensive process of physical robot teleoperation completely obsolete. We are no longer relying on static storyboards. We are plugging our AI directly into the raw motion capture feed of reality. Thanks for listening, and we'll catch you on the next deep dive into AI paper slop.